Well, thanks for inviting us today. We were challenged with demonstrating some innovation around heat exchangers. And I want to challenge your paradigm today that generally in industry, shell and tube heat exchangers are used extensively throughout heat exchangers still today. In colleges and universities, when people teach chemical engineering, we still talk about shell and tube heat exchangers. Even in our code, CSA B51 talks about heat exchanger being greater than 6-inch diameter before it becomes a pressure vessel. So in our heat exchanger world, I want to challenge your paradigm a little bit about heat exchangers and shell and tube heat exchangers. So first question, what do you see on the screen? Who sees something? What do you see? A duck and a bunny. Fantastic. Most people see one or the other. But yeah, there's a duck and a bunny. So I'm looking to challenge your paradigm shift away from thinking of shell and tube heat exchangers as the best heat exchanger specifically for refrigeration. Shell and tube heat exchangers are large compared to a plate and frame heat exchanger. Shell and tube heat exchangers are less efficient. Shell and tube heat exchangers mean more refrigerant charge. Shell and tube heat exchangers have a slower response time, a process response time. And shell and tube heat exchangers need a lot more maintenance space. There's a lot of heat exchangers used in refrigeration systems. So my first question today, you've all been given this lovely sheet here. How many heat exchangers are on this piece of paper up here? There is a prize for the first person. Anybody?
We hear 3 here. 3. We hear 4. 5.
I hear a 5. Any advance on 5? You get the prize. Here's a heat exchanger. Yeah, there are 7. Many of you might forget the pads. There's evaporators, condensers, there's oil coolers, and pads. So there's 7 on that diagram. And this slide just is it's a pH diagram of a refrigeration cycle imposed on a pH diagram. It just shows you there are many opportunities to use heat exchangers in refrigeration systems. I'm just going to turn the presentation over to Grecia, who's going to talk to you about some developments in the business of heat exchangers.
Thank you. So, okay, so here are the trends for the shell and tube. So as you can see, in 2010, we roughly have a 28% using shell and tubes, while in 2015 it decreased to 25%, while the plate heat exchangers are increasing by 1%. The trends as well talk about minimize ammonia or freon charge, safety issues, and using technology to improve the systems, and as well heat recovery. It's very important nowadays. The solution, it's a plate heat exchanger. This is actually our new heat exchanger, TK20. We just launched the TK20 with 8-inch port for, let's say, 120 tons to 150 or even higher capacity. As you can see, all the construction is bolted.
So the technology ALFA LAVAL has is a lot in pressing materials. Until the 1960s, ALFA LAVAL actually used to press body parts for Volvo. So we have a lot of technology in shaping materials in ALFA LAVAL. But the main technology we have in the plate heat exchanger, the area is getting the full distribution across the plate pack. And then here you see what we do in a semi-welded heat exchanger is take two plates and weld them together to form a cassette. So the refrigerant running on the inside of the cassette, the only gasket that would be seen by the refrigerant would be the ring gasket, which you just saw. The field gasket is on the other side and is typically on the glycol or brine side. We have a separate ring gasket groove, which differentiates us from other manufacturers who actually have the gasket sitting on top of that weld. And the new TK20 is part of our range of heat exchangers, semi-welded heat exchangers we have for especially the industrial ammonia business, but also CO2 business, which is a growing refrigerant that's going to be used in North America more and more. Which I'm pleased to say that ALFA LAVAL is taking a leading role in, and Cimco has taken a leading role in North America around CO2 use.
Okay. So the question is, why plate heat exchangers? First of all, it's a low investment cost. We have less heat transfer area due to high thermal efficiency and low material consumption. It's a low-cost future for expansion. You can add or remove plates as soon as you have a bigger load. We have as well flexible construction and bolted frames. We have low installation costs, low weight, low footprint, compact design, less space required, and less investment in piping. On the other side of the slide, you can see the difference in the maintenance space for a shell and tube, while the heat exchanger will be 1/10 of the space you're using on a shell and tubes. So basically, the total weight operating tons on a plate heat exchanger will be 19 versus a shell and tube that it's 136. So floor area, installation, and maintenance will be between 14 to 21 versus 105 to 190. It's quite big difference. And here we have a slide with a picture showing the same duty with two different heat exchangers, a shell and tube and a plate heat exchanger. And as you can see, it's a very big difference in space requirement for plate and frame than shell and tubes. Why we can have a smaller heat exchanger to achieve the same heat transfer? It's because we have higher heat transfer and close temperature approach, while in shell and tubes you can only just go in this part of the heat exchanger. We have useful heat on a plate heat exchanger. We can go as close approach as 1.2 degrees. And well, if you have, in the case of the ice rinks, if you have a fixed flow rate on the brine side, then you the useful heat reflects on the returning temperature to the heat exchanger, which for ice rinks is normally between 2 to 3 degrees, depending on the application. So yep, we can reduce as well investment in pipework, pump, and valves. Again, why plate heat exchangers is easy to regulate due to low hold-up volume and quick response time. That's very important, and less risk of process problems. It's environmentally efficient, high efficiency, high degree heat recovery, low material consumption, and less risk of unplanned stops. While we have gaskets, and you can easily dismantle a heat exchanger and change gaskets and put it on place and start again the system. And we have as well so many different plate materials that we can use. For example, for brine, we can use SMO or titanium, while in glycol, we normally use stainless steel 304 or 316. Low maintenance costs, as I mentioned before, we can easily dismantle and get full access to the heat transfer area. We're going to talk as well about the high turbulence and how it will reflect in a low fouling. So we will get longer operating periods. We have as well the glue-free concept. So we have the gaskets are clip-on, and there's no need for you to put glue on them. We have bearing boxes, locking and guide washers to get easier dismantling. Plate locking and stop on guide bar for good safety at service. Rollers on large units as the TK20, and spare parts list and plate hanging list is delivered with the unit. So overall, quality plates, gasket, groove, and fastening means longer lifetime for you. And here's a video of anatomy of a plate heat exchanger, how it's constructed.
So on a semi-welded heat exchanger, there are very little welding. Obviously, there's the welding that goes on of the plates themselves to create the cassettes, as we call them, and then every other item of the heat exchanger is actually a bolted construction. It's handy if we need to get it into tight spaces. We can dismantle it, take it in parts. We can quickly solve problems with heat exchangers by adding plates, changing plates, or even removing plates as necessary. There are plenty of examples where we've been called to site and solved the problem for the customer the same day.
We have various plate geometries. We have two different types of plates depending on the chevron angle. We have a low theta and high theta. I'm going to talk a little bit more here. We have low turbulence and pressure drop, medium, and high turbulence. So we have three different types of plates. If we put together one low turbulence and one high, we form an M channel, and this will help us to design a specific heat exchanger for your application. So we balance the turbulence we need to achieve the heat transfer and the pressure drop that the heat exchanger will cause in the system. And the advantages of that will be efficient heat transfer, high wall shear stress, variable thermal length, and strong construction. And the benefits as well is increased heat recovery, low fouling, because with the turbulence we are creating velocity as well. So we have a low fouling in the plates. Optimal design, especially designed for your application, and insensitive to vibration. This is a very important slide. Laser welding eliminates 90% of the gaskets in contact with refrigerant. That's very important. Patented distribution area. That will mean that the pressure drop you have in this side will be the same as on this side, and by that we can optimize the usage of the heat transfer area. Clip-on gaskets, so you don't really need to care about the glue anymore. Double gaskets in port area, so this will be 1 and this will be 2. Eliminate cross-contamination because the leak will manifest to the exterior.
So what Chris is just saying is here's the ring gasket, which is isolating the refrigerant. Here's the field gasket, so inside here would be the brine side, And here is effectively a leak path. So if there was a leak across the gasket, there would be an external leak before you had any possibility of getting cross-contamination of your fluids.
This is a very big advantage of the plate heat exchangers. You might ask, what will be the difference between an all-welded solution to a plate and frame heat exchangers? The thing is that with the gaskets on a plate heat exchanger, we can handle fatigue, while in a welded solution, you will have a crack, and sometimes you need to replace all the unit. And thanks to the elasticity of the gaskets, there will be no thermal fatigue problems, and also PHE can take a freeze. We don't want to have that, but the PHE can take a freeze. We have codes and accessories, ASME design, PED, and design pressures up to 800 psi, operating temperatures down to minus 49 F. We have accessories, heating and cooling insulation available, drip tray, and as well we have strainers, strainer ports that we can put on a heat exchanger on the back. Application, we have here chart showing the typical 72 tons ice rink with calcium chloride and ammonium. The brine is coming at 19 and going out at 16 Fahrenheit, and we're evaporating at 12 Fahrenheit. This is a typical application. We can see that the surface we need with the plate heat exchanger is 387 square feet, while it's 4 times higher with the shell and tubes. We can see that we use titanium plates, and shell and tubes is normally carbon steel. The velocity is quite higher on a plate heat exchanger because we need to create the turbulence to achieve the heat transfer. Pressure drop on the ammonia side is 0.33, while in shell and tube is 0.62. This is a very important fact that we take into account while we design a heat exchanger. And well, on the brine side is higher on the plate and frame heat exchanger. Fouling factor that we consider is 0.0002, while in shell and tubes is more than double. And the reason why is because we create the turbulence, then we will expect low fouling in the heat exchanger. The heat transfer coefficient, as you can see, is 4 times higher on a plate heat exchanger. The dimensions, as you can see, as you saw in the picture, are very, very different. To achieve the same heat transfer on a shell and tube, is two passes are needed, while one on the plate and frame. And the price radio, we compared a price of a plate and frame titanium plates with the carbon steel shell and tubes, and the shell and tubes is 27% higher than a plate heat exchanger. The connection size is as well 4 inches on a plate heat exchanger and 8 inches on a shell and tubes.
Maybe it's worth mentioning that ALFA LAVAL does make shell and tube heat exchangers as well. So those figures are our figures.
Yes. This is the capital cost of the plate heat exchanger versus shell and tubes. You can see, well, normally the shell and tubes are carbon steel constructed, but as special requirements for stainless steel and titanium, the price goes exponentially higher. And on a plate heat exchangers, there are those two. We have even lower price than a carbon steel construction. This is very important, as I mentioned. Not all the heat exchangers are designed in the same way. So in our partnership with Cimco, we take into account the pressure drop we're creating on the refrigerant side. And by that, we consider, while we are designing the heat exchanger, to maximize the energy efficiency and to lower the power consumption. So this is an example. By achieving a low pressure drop on ammonia side, we can increase the COP and reduce the refrigerant charge. So this is an example. If we increase the evaporating temperature because of the pressure drop we are creating, then we can increase the evaporating temperature, let's say from 10 to 12, and we save power consumption of the compressor around 3 to 4%.
Just go back to that slide, because I think one of the important things, ALFA LAVAL is a component manufacturer. We're specialists or experts in the plate heat exchanger. I just wanted to point out that the importance of having a system owner or a system responsible company like Cimco in the picture. When we select our heat exchangers, which we do for each and every duty, so every consideration is taken into account for the opportunities to conserve energy, use less charge, make the system more safe and things like that. But not even all plate heat exchangers are designed the same way. So the way that we manage the pressure drop across the system to achieve those things of minimum ammonia charge, low pressure drops, and the most efficient system, ALFA LAVAL cannot do on its own. And we rely, or should I say, I think Cimco rely on ALFA LAVAL to play our part in delivering to you the most efficient system. We cannot deliver that on our own. So when you're comparing even plate heat exchangers, I would say that your choice of the partner that you would use to install a system in your facility is critical for you to actually gain those efficiencies which are achievable with today's technology.
Implementation. As you can see, map of Canada and all the heat exchangers we have installed. More than 1,300 heat exchangers installed so far in Canada. You can see mainly on Ontario, Quebec, Montreal, Halifax, Nova Scotia, but as well on the BC, Alberta, and Winnipeg.
So this is just plate heat exchangers operating in refrigeration systems. Across Canada, we've actually got more than 40,000 heat exchangers installed. ALFA LAVAL is actually a company that started in 1883, so we've been at it a while, and the plate heat exchanger was introduced in the 40s. So there's a lot of heat exchangers, plate heat exchangers, already in operation in Canada. But these 1330 are actually working in refrigeration, and most of them actually installed by Cimco. So I said I wanted to challenge your paradigm. I hope we've challenged your paradigm. It wasn't just your shorts riding up, I hope.
Hi, I'm Bob Davies of Micom Canada. Just wanted to let everyone know I had a great time at Cimco Innovation 15. It was very beneficial, I think, for the arena operators and also as a supplier to be able to go ahead and enjoy the company of like companies, and basically very happy with the outcome of the event.
So I guess overall everything went really, really well today. I'm very pleased with the turnout. I was actually quite impressed with the level of questions that were coming from the audience, and how engaged they were with the content. And I really think some people are going to act. I think they're going to really look to innovate their facilities and try some of these new products out.